Well, this is the last of Chapter 10. We're going to start with an example of a discrete random variable. We're going to look at rolling two die. Our discrete random variable is the number of dots counted when you roll a die 2 times. So to the left of the screen, you see the discrete probability distribution. In the very left column, you see our random variable equaling a certain number. And we can actually see in here the sample space of when you roll two die. So these are the values. You count the dots on the two die, and that's the value the random variable can take. So if I look at the upper left-hand corner, there you see if I roll a 1 for each die, the total number would be 2. And we see that only one time, and that's how the probability is 1 out of 32. Then I see 2 and a 1 and a 1 and a 2. Add up those, that's 3. I see 2 of those, so that the probability of rolling a 3 is 2 out of 32. Then I go for 4. There's 3 of those, so that's where I get the probability 3 out of 32. I do the same thing for 5, where I see 4 out of 32. 6, I see 5 of those, so the probability is 5 out of the 32. 7, I see 6 of those to get the 6 out of 32 as my probability. I see 8, my random variable 8, and the probability that I roll an 8 would be 5 out of 32. With the random variable equaling 9, the probability of that, I see 4 of those out of 32, so the probability that x equal 9 is 4 out of 32. 10, there are 3 of those, so the probability that my random variable is 10 is 3 out of 32. I see 11, there's 2 of those, and the probability that my random variable equals 11 is 2 out of 32. My random variable equaling 12, that's the very last lower right-hand corner, I only see 1 of those, so the probability of rolling a 12 is 1 out of 32. So now we see the total discrete probability distribution. And we can ask questions like, what's the probability of rolling a 5 or a 6? We will just add those two probabilities together, the probability that x equals 5 plus the probability that x equals 6, and that would give us the probability 9 over 32. Now let's look at continuous random variables. So continuous probability, we're going to look at intervals of outcomes. We cannot assign a probability to each individual outcome because there's an infinite number of outcomes. So probabilities are assigned to intervals of outcome by using areas under a density curve. Now a density curve has area exactly 1 underneath of it, corresponding to a total probability of 1. And of course, remember, we did learn that in Chapter 3. But let's take a look at another continuous random variable. We're going to look at random number generators. They give outputs or digits that spread uniformly across the interval of 0 and 1. Or rather, we're using a uniform distribution as our probability model. So we can talk about probabilities of less than 0.05. You would just take 0.05 times 1. We could talk about probabilities greater than 0.08. Well, the distance from 0.08 to 1, the way we find that is we say 1 minus 0.8. That gives us a distance of 0.2. So the area would be 0.2 times 1. So the probability that x is greater than 0.8 is 0.2. So the example that we see here on this slide, it wants to know what's the probability of x being less than 0.5 or x being greater than 0.8. Well, we just add the two probabilities we just figured out. Now it would equal 0.7. As I said, Chapter 3 was very important. And again, we look at the normal probability model. And we're going to look at it as being probabilities. So the normal distributions are these probability models. So we use the standard normal table to find probabilities. And those techniques are exactly what we used in Chapter 3. So Table A, the areas to that left of the Z, are probabilities. We talked about them as being proportions in Chapter 3, but remember, probabilities are just proportions. So the areas to the left of that Z are probabilities. So let's take a look at this example 10.7. in your book, it says, and you can read it, but these are what they say. The probability of seeing a 1 is 0.301. So we have probabilities for the digits from 1 to 9. So we can ask for probabilities such as, what's the probability that x is greater than or equal to 6? So we look at the probabilities of 6 plus 7 plus 8 plus 9. So we get those right off the chart, add those together. So we'd say the probability of seeing x greater than or equal to 6 is 0.222. Now this was a probability model. We said that it was, but you could make sure. Are the probabilities numbers between 0 and 1, including 0 and 1? They sure are. In fact, they're numbers between 0 and 1. And when you add up the probabilities, they do equal 1. Now if we take the probability that x is greater than 6, then we can't include 6. So we're going to get a smaller area because we're going to add 7, 8, and 9 to get a probability of 0.55. So that's what that example said. And we could ask for other things, like what's the probability that x is less than 3? Well, that would just be the probability that x equal 2 plus the probability that x equal 1. And I get those numbers right off the chart and add them together to get 0.477. So let's look at 1013, problem 13, and let's look at this. We have this probability. Is this a probability model? Well, first of all, the probabilities are numbers between 0 and 1. In fact, they are numbers between 0 and 1. When we add them up together, we get 1. So this is a legitimate probability model. So it reached our two conditions, that the probabilities are probabilities, that is, numbers between 0 and 1, including 0 and 1, and also adding up the probabilities of that sample space equals 1. Now they say describe the event x is less than 7 in words. That means we want to know the event of having 0, 1, 2, 3, 4, or 5 days out of the 7 that a person worked out. So what's the probability that x is less than 7? Well, I hope I included 6 in that, so it's 0, 1, 2, 3, 4, 5, 6. So what's the probability that x is less than 7? Well, I could add up the probabilities of 0, 1, 2, 3, 4, 5, and 6. Or I could use the complement rule, 1 minus 0.02. So what's the probability that someone works out less than 7 days? Well, they've got a 0.98 chance of working out less than 7 days. And personal probabilities. It's the degree to which a given individual believes an event in question will happen. So it's a personal belief or judgment. It's used to assign probabilities when it's not feasible to observe outcomes for a long series of trials. So here are some examples of personal probabilities. Well, this concludes Chapter 10, and we will start Chapter 11 very soon. Thanks.